Okay, here we go with the last homework review video. I'm doing this a little bit early before the deadline for this assignment, just so people that have the exam tomorrow can use this to their advantage if they choose to do that. So again, the homework is not due until Monday night, but I'll just go ahead and get this recorded now for the benefit of everyone. The scores so far have been pretty good, but there are a few problems that we struggle with a bit that I want to go over now. We had 50% success rates or less on the following. Alright, so the first one deals with enthalpy of vaporization. We have 577 gram sample of a particular compound with a molecular weight of 124, and this requires 7 joules of heat to vaporize. What is delta H of vaporization in kilojoules per mole? Sorry, I left out part of this question here. So we're looking for delta H of vaporization in kilojoules per mole. So we're going to have, it's going to be the heat required to vaporize the sample in kilojoules divided by the moles of compound. So our heat here is 7 joules, so if we want to put that in kilojoules, it's going to be 7.00 times 10 to the minus third kilojoules. So we convert joules into kilojoules, and then we're going to divide that by moles of compounds. So the moles are going to be, we have 577 grams, and then 1 mole of this compound, we're told, has a mass of 124 grams. So we have 4.65 moles. And I think this was a multiple choice question, but the answer you should have gotten and chosen is 0.00150 kilojoules per mole. Okay, so a very small value, so this is presumably a substance that has very weak intermolecular forces, but it's really just dividing the amount of heat required by the moles of the compound, making sure to take care of units, which should be kilojoules, to match with the answer choices. Okay, so that's how we calculate enthalpy of vaporization. It's just defined as the amount of heat required to vaporize 1 mole of substance typically. Sometimes it's given to you in grams, but usually it's per mole, and so to do that we just take heat divided by moles. Alright, we had a couple problems dealing with cubic unit cells. I'll let the cat out of the bag and say we're not going to go into quite this level of detail on the final exam, so the questions will be a little bit simpler, but I think that, as I said in class, and as I hope you agree with, knowing some of these structural features in in a higher level of detail helps you understand the structures better, and it makes those easier questions we're going to ask even simpler to analyze. So in this case, we're looking at relationships between the metal atom's radius and the face diagonal. So if we sketch out a primitive cubic cell, if we're looking at one face of our cube here, so again, this side length here is what we call A. And for a primitive cubic cell, we just have atoms in each corner, and they're all touching each other. So you have sort of this picture here. Okay, so not the best drawing, but I think you get the idea. We have atoms, spherical atoms in each corner. So as we go across one of the side lengths, we have the radius of one sphere plus the radius of another. So the side length A for a simple cubic structure is equal to 2 times the radius. But here we're looking for the length of the face diagonal, spelled incorrectly, but that's what we're looking for, is face diagonal. Distance between opposite corners of a face. So we're looking for this distance here, which I'll call D. So D, the length of a face diagonal, is equal to A times the square root of 2. That comes from Pythagorean theorem, which is going to be equal to 2 times radical 2 times R. So we're going to take 2R here, put it in for A, and we get a relationship that the face diagonal is 2R radical 2, which is just going to be 2 radical 2 times the radius, which is given as 102. And we should get something like 488. Let me make sure that's correct. We get 288.5. Okay, so that's going to be the distance D in this picture here. Okay, so knowing the structures in and out sort of helps us derive these relationships, from which also require a little bit of knowledge of geometry. And then we have another one here that's probably maybe a little bit more complex, which is a face-centered cubic structure. So here the metal atoms are in a face-centered cube, and we're told that the radius in this case is 150, and we want to know the length of the edge of its unit cell in picometers. So here we're actually calculating A. Now in this case there's not as simple a relationship, because if we think about face-centered cubic, this is going to be a little bit harder for me to draw, especially with my marginal artistic ability, so I apologize in advance. But for face-centered cubic, you sort of have this situation. You have a little bit of a gap between each of the atoms in the corners. Then you have the one in the center that sort of touches all of them. So it's not quite to scale, perhaps, and not the best drawing of all, but at any rate, the two, the radii don't touch each other. So if we go across one side length A, we have this gap here in the middle. We don't really know how big that is, but we do have a pretty simple relationship, because along the face diagonal D here, we have radius. We have two radiuses to get through the center atom, and then another radius in the corner. So that means in this case our diagonal D is equal to 4 times the radius, 2 times the diameter, 4 times the radius. And as we saw in the last problem, using Pythagorean theorem, that's equal to A radical 2. So here we're solving for A, which is the length of the edge. That's what A represents. So A is going to be 4 over radical 2 times R, which is 2 radical 2 times R. And so what we get then is that it's going to be 2 radical 2 times the radius, which is 150, which is 424.3 picometers. Alright, so again, it's using relationships between the side length, the radius, a little bit of geometry to get the relationship between the side length and the atomic radius. So again, those last two questions are more details than we'll need for the exam, but I think it does help to really think about these structures in detail as we evaluate some of the things about them that we are expected to know. Alright, so in this problem here we have a relationship between vapor pressure and temperature. So we're talking about Freon 113, which we give the formula for. It has an enthalpy of vaporization of 27 kilojoules per mole and a normal boiling point of 48 degrees Celsius. What is the vapor pressure of Freon 113 at 22 degrees Celsius? We're also giving the value of R in joules per kmol. So this is a problem where we have two temperatures, and we're asking for a new vapor pressure at a given temperature. So we're going to use the one equation we know that relates vapor pressure and temperature. So for a given substance, the only thing that vapor pressure depends on is temperature. Vapor pressure also depends on the nature of the substance, but if we're just talking about one substance, there's one equation relating vapor pressure and temperature. Now the form that your book uses is this one here. Let me make sure I write it the same way that your book does. Alright, so it's going to be the natural log of P1 over P2 is equal to the enthalpy of vaporization divided by R. So if we're going to use this equation in any level of accuracy, we need the enthalpy of vaporization, and it's going to be 1 over T1 minus 1 over T2. Sorry, I have those switched. T2 minus T1 if you write it this way. So there are a few different ways to write this equation that are all equivalent. This is the way your book does it, so that's what we're going to use to help us in this problem. So we need to assign, P1, T1, P2, T2. It's arbitrary which one you choose is which one is 1 and which one is 2, but they do need to pair up correctly. So if we call this T1, and we call this T2, what we're solving for is the new vapor pressure, which we'll call P2. So T1 is going to be this temperature here, 48 Celsius, which we need to convert into Kelvin for this to work. So this is another equation where everything has to be in Kelvin if we're using temperature. So that's 321. Now P1, what is that going to be? We're not explicitly told the initial pressure, but this is the normal boiling point is 48 degrees Celsius. So at the normal boiling point, remember that the vapor pressure is exactly equal to 1 atmosphere. So our initial vapor pressure that we're considering at the boiling point is 1 atmosphere. So we have this T1 and P1, and then we're going to do for T2, that's going to be the second temperature, which is 22 degrees Celsius or 295 Kelvin. And then P2 is what we're solving for, that's our unknown. Alright, so we get the natural log, we'll start putting the numbers in. P1 is 1 atmosphere. P2 is our unknown. And that's going to be equal to the enthalpy of vaporization over R. Now R is in joules, so we need to make sure we convert our enthalpy of vaporization to joules so that unit cancels out. So 27,000 joules per mole is the enthalpy of vaporization, divided by 8.314 joules per kmol. That allows joules to cancel out. And then finally our temperature terms, our T2 here is 295 Kelvin, and then T1 is 321. So we have a bunch of numbers here on the right side of our equation, which we multiply out. We get 0.892. And then if we want to get rid of the natural log on this other side of the equation, we need to take the exponent of that, or e to that power. So we do that, we get 1 atmosphere over P2 is equal to e to the 0.892, which is 2.439. Alright, and then finally if we solve for P2, it should be less than 1 atmosphere because it's a lower temperature, and we get 0. I don't remember if this was multiple choice or free response question. I think it was multiple choice, but this should be the answer that you got, 0.41 atmospheres. So when you're checking these, we know that the vapor pressure decreases with temperature. So we're talking about a temperature below the boiling point, then our vapor pressure should be less than 1 atmosphere, which it is here. Alright, we have another problem dealing with enthalpy of vaporization. So we have 1 mole of benzene vaporized at a constant pressure of 1 atmosphere and at the boiling point of 353 Kelvin. 30.78 kilojoules of energy is absorbed and the volume change is plus 28.9 liters. What is delta H for this process? Now this question here seems complicated. We're giving you a lot of information, pressure, the temperature, how much energy is absorbed, volume change, all these things. But really what we're asking you here is, do you understand the definition of enthalpy? So when we first introduced delta H, we saw that it's equal to delta E plus P delta V, which is equal to the heat measured at constant pressure. So this relationship here, delta H equals QP, is key because if our process is happening at constant pressure, all we need to know is the heat term, and that's going to give us delta H directly. So if we look at the information in this problem, vaporize at a constant pressure of 1 atmosphere. Our pressure is constant, so we only need the heat absorbed. So we're told that 30.78 kilojoules of heat is absorbed, so that means delta H is equal to plus 30.78 kilojoules, and it's 1 mole, so it's, that's exactly the enthalpy of vaporization, and that's it. So we didn't have to do any calculations in this problem if you know the definition of delta H. Many of us tried to put this P delta V term in, but for delta H we don't need that. If we were calculating delta E at a constant pressure, it would be QP minus P delta V. For delta E we would need to account for the volume change, but for delta H it doesn't matter. If it's at constant pressure, all we need is the heat term QP. Yes, that one was a little bit of a tricky one, but I just wanted to really see, do we understand the definition of delta H and how do we calculate that at constant pressure. Alright, another type of vapor pressure problem is where we're actually going to use PV equals nRT to help us. So we have 255 milliliters of bromine vapor It has a mass of 0.837 grams and is in equilibrium with its liquid at 42 degrees Celsius. What is the vapor pressure in millimeters of mercury of the sample? So for this one here, we have the amount of water of vapor. We have, we have the volume, we have the mass amount, and we have the temperature. So for these types, we're going to use PV equals nRT. We're looking for the vapor pressure. We know, in some sense, all the rest of these. The pressure is just going to be nRT divided by V. So the moles of Br2 vapor, we're told that we have 0.837 grams. We have to remember that bromine is Br2, and that means one mole has a mass of 2 times the atomic mass of bromine, which is 159.8. So we have a total of 0.00524 moles. R is the universal gas constant. We're talking about a vapor phase here. We'll use this value, liter atmospheres per K mole. And the temperature is 42 Celsius, so we have to convert that to Kelvin. So we add 273 to that, we get a temperature of 315 Kelvin. And the volume of our samples is 255 milliliters. We convert that to liters to have the units work out. And we get the volume, or the pressure is going to be equal to 0.531 atmospheres, but we're looking for the vapor pressure in millimeters of mercury. So the pressure in millimeters of mercury is 0.531 atmospheres times 760 millimeters mercury per 1 atmosphere, which is 404. Alright, so I believe this is multiple choice. There should be one of the answer choices very close to that. So for vapor pressure, if we know the amount of vapor, the amount of substance that's in the vapor phase and the volume of it and all those things, the PV equals nRT still applies. So if we're talking about the gas phase of any substance, assuming ideal behavior, we're going to have that equation that allows us to relate pressure and volume and number of moles and all those things. Okay, so the last problem I want to go over is dealt with phase diagrams. So we're looking for the vaporization of X. So remember that vaporization is liquid going to gas. So in this diagram down here, if we're talking about a process of the vaporization, we need to start in a part of the diagram where the liquid exists and move to a part of the diagram where the gas exists. So if we label the parts of our diagram, solid up here in the top left, liquid here in the middle, gas in the lower right, and we want to figure out which of these processes results in vaporization, which is going between the liquid and the gas phases. So if we're at point A, that's for choice A here, we're starting in the solid phase, so we're not going to have vaporization. If we raise the temperature and pressure until we get to H, we're going from solid to liquid. Solid to liquid would be melting. Okay, so in part A we're melting, but we're not vaporizing. Okay, for choice B, we're starting at point F. Okay, so at point F here, we're in the boundary between liquid and gas. So we do have liquid and gas present, but if we raise the temperature and pressure to go to point H, here we're back in the liquid part of the diagram, so we're going to take this liquid-gas mixture at point F, and we're going to convert this completely to liquid. So this is going to be condensation, where we're starting with an equilibrium mixture of liquid and vapor, but then we condense it all as we change the conditions. So that one's not going to be vaporization either. Okay, for choice C, we're starting at point H. So here we're actually starting in liquid phase, but we're going to change the temperature and pressure until we get to point A. So we're going in this direction. We're going from liquid to solid, so that's going to be, fusion or freezing. I guess freezing is a more appropriate term. So here we're freezing the sample. We're going from liquid to solid, so that's not going to be vaporization. Answer choice D, we're starting at point A, so again we're starting in the solid part of the diagram. This one is worded confusingly, but we're going to point C. So here we're going from I guess C is this one here. It looks like a G to me, but we're going to here. So we're going from solid to gas. So choice D is worded confusingly, but remember for vaporization we're going from liquid to gas. Here we're going from solid to gas, so that's going to be sublimation. So sorry about the bad wording for that answer choice, but in net we're just going from solid to gas, so it can't be vaporization. So finally, we only have one more left to see if this is vaporization. We're starting at H, which is liquid, and we're going to point C, which is gas. So here we're going liquid to gas. So this one is in fact vaporization, and that's going to be the correct answer. Okay, so for phase diagrams, you need to know, the three regions of the diagram: solid, liquid, and gas. If you start in one part and move to the other, what is the classification of that phase change? So just to review that really quickly, if you're going from solid to liquid, that's what we call melting. If you go from liquid to solid, that's freezing. So these two are opposite processes, but they have different names. If we go from solid to gas, skipping the liquid phase, that's called sublimation. A term you don't need to know, but if you're curious, going from the gas phase to the solid, so the opposite process, that would be called deposition. Liquid to gas phase, as we said, is vaporization. That was a key for this problem. And gas to liquid, I'm running out of room, is condensation. Okay, so those are all the phase changes. There's 6 of them: melting, freezing, sublimation, deposition, vaporization, condensation. And we can predict on a phase diagram which changes and conditions will bring about all of these types of phase changes. Alright, that takes us to the end, the very last homework review. I hope you enjoyed me doing these reviews. I got some good feedback, so I anticipate I'll keep doing them in future versions of this course. But if there's anything I didn't cover here that you'd like me to go over, please contact me. And I hope you all have a great final exam period and a great summer as well.